So I'm going to talk about crustal strain rates derived from GPS velocities. I'm going to talk about doing that inside a rigid plate. And efforts to do so in the past have had mixed success because of the nature of the problem. And as a result, for instance, there's still debate whether, based on the same GPS stations, there's strain accumulation in the New Madrid seismic zone in the United States or not, which has very big implications for seismic hazard. However, there's also implications for constraining glacial isostatic adjustments, which are typically constrained by vertical motions, but they could also be constrained by horizontal deformation. So a little bit of a background here. In the Nevada Geodetic Laboratory, we try to process all the RINEX data that's available in the world, and we do so currently for more than 16,000 stations. There's a map there. For a large part of those, we use the velocity together with published velocities from campaign measurements to derive strain rates. And you see a map on the bottom here, which are contours of strain rates inside plate boundaries. What's missing here is that a lot part of the world is still white. Those are the intraplate areas that we did not try to model strain rates for because it's difficult. However, as you see on the top, actually most of the GPS stations in the world are inside intraplate areas. So there's a tremendous opportunity here that we are trying to exploit, just simply using the power of numbers. And I'm going to focus on North America today. Here's a map of North America. I'm showing almost 4,000 stations here that we analyze. Most of those are continuous. I want to point out that about half of those, less than half of those, are part of the United States course network run by the NGS, the sort of network that people typically use for this sort of approaches. But there are many more stations out there, and they're shown in red, and they come from Department of Transportation networks, commercial networks, stations that are often not used for geodynamics. But I would argue if you have enough of those stations, then yes, they may be bad and noisy. If you have enough of those, they may be useful. And that's what I'm going to build on here. So one thing that people typically do when they are concerned about glacial isostatic adjustment is look at the vertical velocity field. So that's shown here. On the left is an interpolation that we've done of vertical rates. The scale goes up to about 12 or 13 millimeters per year. And to the right is a prediction based on the I6G model from Peltier and colleagues. And in general, you see that these largely agree, except, for instance, for Greenland, which current uplift is mostly dominated by present-day melting and not by glacial isostatic adjustment. We also see some parts that are subsidence, which are less clear in the isostatic adjustment figure. So this is vertical motions. I like to focus the rest of the talk about horizontal. So the figure here shows a prediction again of a GIA model. The contours show you uplift, and then the arrows you see are horizontal motions. And they're not very high. This is the scale, 1 millimeter. So you have about 1 millimeter per year, in this case, of motion towards the ice in the far field. If we actually want to use observations of that, we have a couple of problems. First of all, if you look at velocities, you like to have a reference frame. Well, it's not clear what the reference frame is if all of the plate is moving. Now, in the past, people have tried to come around that with actually using a model of GIA and establishing what should not be moving and what should. But then you go in a circular fashion we don't like to do. It's better to use the strain rates, because strain rates are not dependent on the reference frame. So it would be good to derive strain rates for the intraplate area, but there's a couple of problems. Strain rates are very low at the level of the noise in the GPS velocities. They're very sensitive to outlier velocities, particularly if stations are very close together, because strain rates is a spatial derivative. So that data, those outliers will just explode in strain rate estimates, and we don't want to do that. So first, to illustrate the problem of reference frame, here I'm going to show you 4 different velocity fields that are the same velocity field, but in a different reference frame. So these are all published. The one on the left is the ITRF 08. This is the previous ITRF model. The stars are the stations that were used to minimize the motion of North America. And yes, that means that all that area in the United States part of North America is indeed not moving, but Canada and Greenland are moving significantly. The one to the right is one that I published a few years ago, where I acknowledged that all of the plate is moving, so therefore I took a couple of stations scattered around and shown by the stars here. And now all of a sudden it looks very different. Same velocity field, just different reference frame. Now you see that the stations in North America, in the United States, move towards Canada, as well as stations in Alaska and Greenland move towards Canada. Here's 2 other ones, also published. The one to the left is the NA12 one, and the one to the right is SNARF. Anyway, same message. Okay, before I'm going to present you strain rates, I'm going to present you a new method to estimate strain rates, which is fairly robust to outliers, but still it turns out to be important to try to get rid of outlier velocities as much as possible. So first of all, we only use data that's 2.5 years in length. Very short time series are not very useful. That limits the number of stations dramatically. I should mention we use the velocities estimated by MIDAS. This is our automated velocity estimator, which is robust against seasonality and offsets. So then we also removed outliers. You can see those here in blue. Blue outlier velocities, red are not outliers. This is based simply on taking a velocity and comparing that velocity with what's predicted from the stations around it, the strain rate and the deformation of that polygon. And you use a certain threshold. And so this is all automated. This works very well. So we get rid of those. In the end, we're left with about 2,200 velocities that we're going to use to estimate strain rates. One other step we do is we do a slight smoothing of the velocity field. So red is unsmoothed, blue is smooth. All of this is important because stations, we have so many stations. This is the good thing. We have a lot of stations, that's very good. But many of them are very close together, which means that the spatial derivative means the strain will explode. So we have to be very careful that we're getting as smooth as possible input. And then we have a new algorithm that we developed. What we're going to do is we're going to, for instance, want to estimate the strain rate at the star here. We do a Delaunay triangulation of the stations, and we identify the triangle in which this point resides. That gives you 3 velocities. In theory, you could calculate the strain rates from it, but that's not a very sensitive thing to do. You want to use more data. But we don't want to use least squares because outlier data that may still reside in the data will still dominate. So what we're going to do is we're going to take a median of a set of strain rates. And what we're going to do is we're going to look one station out from these 3 stations identified. That gives you the blue stations over here. And then create all the possible triangles from those stations. And calculate the strain rates in those. We only do this for triangles that are large enough and not too skinny above a certain threshold. And we want to initially only look at triangles that encompass that point. If you don't reach your minimum number of triangles you want, in our case like 100, you have to go one level out, etc. And then you take the median value of the components of the strain rate and the rotation rate. And without further details, this is sort of what you get. On the right shows the contours of strain rates. These are very small numbers. This green band you see here has strains of about 3 nanostrains per year. Most everything else is less than that. And to the right is everything shown more than 2 sigma, above 2 sigma. So that means that belt you see there is well resolved, A. It also means that most of the strain rates, for instance, in the United States, including this New Madrid area, the strain rates are not above, cannot be resolved above uncertainty. Now, what I just showed you was the second invariant of strain rates. It's more interesting to look at the first invariant of strain rates, which is dilatation. So the contours here show dilatation. Red means extension, blue means compression. So now we see that underneath the former ice in most of Canada, we have red extending, and then that zone of high strain rates that we saw before is all blue, is compression. You can also see this by these vectors. These are the principal axes of the strain rate. It shows, for instance, that the compression here, the black vectors are compressional, are all sort of radial inward, and also shows that the extension in Canada is biaxial extension. That's kind of what you predict from glacial isostatic adjustment. Also interesting is to actually to look at the velocity field. So for every little evaluation point, we do this at 0.25 degree grid, we estimate strain rates, but we also estimate the rotation. And then we take a area weighted average of all those rotations for the whole plate and remove that from the original velocities. We did this analysis in the IGS-08 reference frame. So we remove that, and then you're left with these purple vectors. So these are the intraplate velocities associated with this deformation field. And it shows that most of the United States is moving towards Canada at about 2 millimeters per year, fast. And Greenland is moving to Canada too, 2 millimeters per year, and Alaska too. Everybody moves to Canada. So it's nice there. I didn't hear that. So this is a summary of what I just told you. So we would like to use this ultimately to improve GIA models. And so here's a prediction of looking at this I6G model from Peltier and converting that into strain. And so this here is a comparison of the dilatation. You see the colors and you see the axes. Both of them predict extension in Canada, biaxial extension, like we see too. But this model does not really, and I have to say that the GIA model, we know the prediction everywhere, but this is only done at the same stations for which I did the strain model using the same technique. So I'm trying to make this apples and apples as much as possible. What's missing here is this belt of contraction that goes from the Canadian plains all the way to the Great Lakes and then wraps around, that we see very clearly. It's not there. Yes, strain rates here are contractional. You see the black vectors here is moving towards each other, but the rate is much lower. You see the model predicts contraction here, but it's sort of spread out all across Greenland, and we see the signal very well constrained between Greenland and, say, Baffin Island. And here's the same comparison, but then looking also at the velocities. So you saw the one on the figure on the left before. This is the same predicted, and you see a slight northward motion of stations in the United States, but it's less than 1 millimeter per year, and we predict about 2 millimeters per year. So this fast northward motion that we see, of course, is directly associated with this contractional strain band. You need that to explain the difference between Canada and the southern United States. And that is missing in the GIA model. So this new result is the most robust strain field we can come up with. And this has potential for seismic hazard. But I think it has tremendous potential also for GIA constraints. Those models can be very sensitive to the viscosity of the lower mantle. And that would really affect your far field horizontal motions. So clearly, while there are some similarities between what we observe and what we predict, and we also saw that for the vertical motions that I showed you in the beginning of the talk, there are some big differences that still need to be explained, and that will be the next step of this work. Thank you very much.